Okay. Good afternoon. My name is Natongo Jocelyn Madrin, and this is group 1 presenting indoor air quality monitoring. And here we are basically predicting the quality of air within a building. We are looking at the pollutants such as carbon dioxide, carbon monoxide, PM10, PM2.5, among others. Our keywords are, our title is Reinforced Quantum Feature Learning for Indoor Air Quality Monitoring with Ensemble Knowledge Distillation. Our keywords are indoor air quality, air pollution, quantum machine learning, graph attention networks, and knowledge distillation, and ensemble learning. The contents of the presentation are introduction, related work, problem statement, research questions and objectives, research contributions, methodology, dataset description, results, conclusions, anticipated limitations and counteraction plan, references, and the acknowledgement. When we go to the background, here they're basically showing us the transition from traditional fuels to the improved cooking systems. Here, the traditional fuels, for example, we talk about using of firewood, whereby they cause and that results to high levels of indoor air pollution. But when we look at the studies, we see that improved cooking systems can significantly reduce pollutant concentrations, and there we can use ovens. But the widespread adoption remains a challenge since not everyone can afford it. And we are going to use advanced computational methods such as quantum machine learning, graph attention networks, and knowledge distillation. And this will be explained in the next slides. We continue to the related works. And here we are saying that indoor air quality monitoring is crucial for health and environmental safety. So traditional sensor-based approaches such as gas sensors and optical particle counters face limitations. Here we are looking at the challenges, what was researched, and the challenges first. So here we are saying that there were the traditional sensor-based approaches, but then the adoption of the machine learning or the modern technologies such as the machine learning models, which we are seeing the CNN, the LSTM, ensemble learning for indoor air quality monitoring, and our work integrates ensemble learning with quantum machine learning to improve indoor air quality forecasting. When we continue to the recent trends, these are the trends, like the things that are on, and there we are seeing that it is indoor air quality monitoring is rapidly evolving due to the technological advancements in machine learning. And here we are using the machine learning models such as the graphical attention networks. Here you will see the visualizations. We have knowledge distillation, where we have the transfer of knowledge from the large machine learning models to smaller, efficient models. We have the quantum machine learning, which uses quantum advanced kernels and variational circuits. Yes. And the other trends the other emerging trends in indoor air quality monitoring, as they are listed below: multimodal data fusion for privacy preserving monitoring, energy efficient indoor air quality models using tiny ML frameworks, among others. Thank you.
Thank you very much. I'll be taking you through, and by names of Katindiran, I'll be taking you through the literature review of our project. The literature review here, specifically, we look at first of all, the crucial factors that have, like, what are the crucial factors of the indoor air quality, and some of the advancements within this system. Then here, specifically, methods that are used, the traditional methods were used, the sensor drift, the environmental noise, and high maintenance costs and limited scalability. Those are the sufferings of those methods, the traditional sensor methods. Traditional sensor methods, like specifically the environmental noise, the suffering of the environmental noise. Here, specifically, we mean the amount of pollutant within the environment, and the high maintenance costs. How will you be able to go for health practices or for health treatments? So within the advancements, we have like the IoT. These ones have been able to predict or monitor the real-time accuracy, scalable air quality predictions. We have the evolutions, the traditional sensors based, and the challenges such as the challenges, reliability, data privacy, and computational remain. We go to the problem statement. Going further to the problem statement, here the problem statement specifically, we have the domain application problem, the computational problem. The domain problem specifically, we deal with how has air quality affected the environment. We see the pollution, the carbon monoxide, the increase of carbon monoxide, the increase of carbon dioxide, the increase of the volatile organic compounds, how they have affected the environment, especially human health. Then the computational problem, how has it affected the models? How has it affected the computational area? The high dimensional data processing, the limited label data, spatial and temporal dependencies, model complexity and efficiency. Then we also have the real-time adoptions. All of those ones have been challenges faced by those computational, like the computing part within the air quality. Going further to the research questions, here, research questions and objectives, specifically, we develop a machine learning model for predicting indoor air quality. We implemented an efficient feature extraction method for handling high dimensional data. We evaluated the proposed IAQ. Then we integrated the IAQ monitoring system with the real-time adoption. Going to the research contributions, we implemented an efficient feature extraction technique to handle dimensional data. We evaluated our proposed IAQ monitoring system. Then we integrated the real-time adoption mechanism into the IAQ monitoring. Then we also deployed a machine learning based IAQ model that utilizes multi-sensor data for accuracy and forecasting. Yeah, I shall allow the next the next discussant. Yeah, thank you very much.
Hello, my name is Navasiri Nicole, and I'm going to be taking you through methodology, the dataset description, and output or expected results and discussions. So basically, the methodology, this is the machine learning workflow for air quality monitoring, covering data collection, data pre-processing, the EDA, model development, model evaluation, and model selection. So basically, we need to collect the data that we needed to train our models on, and that's what's done during the data collection phase. Then we need to pre-process our data to make sure that it's clean, to be ready to be trained by these, to be ready to be used by the models we're going to train. And then we did this through an EDA. Just for context, I'll mention what an EDA is. In full, it's an exploratory data analysis, and this is a fundamental step in the data analysis process that involves summarizing and visualizing data sets to uncover underlying patterns, trends, and relationships with the data before applying formal modeling techniques. And under the EDA, we have various steps, which is understanding the data, identifying patterns, detecting outliers, checking assumptions, and then guiding further analysis. Then after the EDA is done, this is when we train our models, which is under the model development. And then after we've trained a bunch of models, we evaluate them. And based on the performance, we select the best model. Then we're going to go to the dataset description. And before we go to the dataset description, I'm going to be mentioning why we chose the dataset that we're using for our work. And basically, indoor air quality refers to the condition of the air inside buildings and structures, and it can significantly impact health, comfort, and well-being of occupants. And our dataset was sourced from GitHub and indoor sensor networks. It contains data collected from various sensors monitoring air quality and environmental conditions within a specific location and environment. The dataset is organized with the following features, which is the timestamp, carbon dioxide, humidity, particulate matter, 10 and 2.5, and temperature. So going to the output and expected results and discussions, we have the carbon dioxide levels that fluctuate over time, and then the concentration of the particulate matter 10 particles over time, and then the concentration of particulate matter 2.5 particles, and then the fluctuation of humidity levels over time. And the reason these are our results is because the goal of our work is to monitor the air quality within buildings, structures, and etc. And the only way we can do that is by knowing the concentration of pollutants over time. And these different pollutants have a way they affect the health and well-being of occupants. And that's why our expected results are the concentrations of these different pollutants over time. And here are some more results. And then we also have tables showing the features, timestamps, carbon dioxide, humidity, particulate matter, and then temperature. Then we also have the visuals from the EDA. And there is more output, as you can see. Thank you. I'd like to let my next colleague take over. And yeah.
Hello, everyone. I'm Irene, and I'm going to take you through I'm going to continue from where my colleagues have stopped. So here we have the output of the moving average for our air quality trends. And this graph, this figure, illustrates the moving average of temperature levels over a 5-day period. And this is offering insight into consistent temperature trends over time. Then, for the conclusions, we see that indoor air quality affects our health and well-being, and the poor indoor air quality causes allergies, nausea, and long-term health problems. And here in the present study, we see that science are working on better ways in order to monitor and identify the different sources of pollution. And most studies are taken over, like they are frequently in schools and homes. Then the monitoring helps us to understand what is polluting the air inside the buildings, and high pollution levels come from burning wood, then charcoal, mostly during the cooking and heating. And then the other thing about the conclusion is that they are the traditional methods, which are a source of apportionment, more so like when you're creating the data set, you need to have the paradigm in the source of identification. And we also have that we identify sources more accurately, and through that, we can be able to prevent and react more so on stopping pollution before it happens, and also reducing pollution once it is detected. Then the limitations, we have that many studies focus on homes and schools, and they leave out a few more places, for example, museums and hospitals, which have more people for monitoring in order to help them monitor the indoor air quality so that to prevent them from getting the bad effects, the bad side effects of the bad air, the bad indoor air quality. Then we also see that there are low research studies in some different features. For example, the carbon monoxide and nitrogen dioxide. And most of the time studies are taken on the PM 2.5 and PM 10, leaving out the rest. And this leads to real-time source identification, enabling the implementation of reactive mitigation measures. Then, we also see that the diagnostic PAH isomer ratios are not adequately considered for accurate appointment by some studies. Then we have our next steps, where we see that we are planning to have enhanced feature engineering by identifying and integrating new relevant features, as well as normalizing and standardizing data for better consistency. Then we also have advanced model training, where we experiment with diverse algorithms and also perform cross-validation for robust generations. Then the optimized hyperparameters, we use the grid search, random search, and Bayesian optimization, as well as the fine-tuned hyperparameters for optimal performance. And the continuous monitoring and training, we see that we implement real-time performance monitoring and also set up automated alerts for anomalies and data drift. Then the effective visualization and reporting, we usually develop intuitive dashboards, like dashboards which are attractive to the customers or the users, and also generate comprehensive reports for stakeholders. Then we also have the references, some of our references, and they are here where we have, there are only 10 here, but in the concept net they are detailed. Then we also have our acknowledgements, more so to our lecturer, Mr. Galwango, who has been our advisor, and he has been there providing us continuous support through his patience and guidance throughout this project. And we are also grateful for the teamwork that has been in our group as we try to develop up this project. And we also finally extend our appreciation to everyone who in any way or the other way helped us in the completion of this work. Thank you for listening. This was Group 41. See you next time.